Okay, so Math 156, homework 8, number 39. So we're interested in the following problem. We want to sum the number -1 to the power n plus 1 times 3 divided by n squared. And we want to find the first 6 terms of the series, n equals 1 ... 6. So if I write sum with a capital S, it's just the statement of the problem. And because this is a command that has 2 versions depending on whether you use an uppercase or a lowercase s. So here I'm using a lowercase s, and this is the answer. And so I have the first 6 terms of the series. This is what it is. Is that the one you wanted me to do?
Yes, and number 41.
So for problem 41, it says to use theorem 915 to determine the number of terms required to approximate the sum with an error of less than 1/1000. So you have to see, what does theorem 915 say? It says that, so this is an alternating series. Of course, the terms go plus, minus, right? And it converges because these terms are getting strictly smaller in absolute value and going to 0. And the remainder, so so this is what the theorem says. If you take the absolute value of the sum of the series minus the partial sum, this means the sum of the first n terms, that's going to be less than or equal, that's the remainder, and that's going to be less than or equal to the n plus first term, right? That's what the theorem says. Theorem 9.15. So here we have a series, and we want to know how many terms we need until we get a term which is less than 0.001. Right, so in this series, maybe I should write it a square brackets n. That's maple notation. So remember, the sum of the first n terms of the series is this sum from 1 up to capital N for whatever So this is how you write the first capital N terms of the series. And the nth term, AN, is this. Right? So this is the partial sum of the first capital N terms of the series for any number capital N. And for every little n, the nth term is equal to this. These are the terms that we're summing up. And we want to know when is the error, S minus Sn, smaller than 0.001. So we want to find an n, which is for which this in absolute value is less than 0.001, 1/1000. Here, let me just do an example. What is, let's say, A20. Let's make this a function. So this is A of 20. What is this? Oops, this should be A. Okay, so A is this function. And A of 20 is minus 3/400, or 0.0075. What I really want is the absolute value of this. So let me see what happens if I put in absolute value signs as opposed to, yeah. So this is 0.007. This is not less than 0.001. So let me just try a few other numbers and see what happens. If I let n equal 30, it still is a little bit too big. Suppose I make this 40, still is bigger than 0.001. Suppose I make this 50, still is bigger. 60 point, well, all right. So let me just explain. We have this series, and we want to know how many terms we need to take, because we can always add a finite number of terms. There's no calculus there. But you want to know how many terms do you need to take so that the partial sum of that many terms of the series is within 0.001 of the correct answer. So, and the theorem says that if an plus 1, so that the true infinite convergent series, the limit of the series, minus the partial sum, is going to be less than the n plus minus the sum of the first n terms is less than the n plus first term. All right. So let me also make this a function. So S is the function that takes this, the partial sum of this series. So for example, oops. S of 6 let me make this a lowercase s. So this is giving us the first 6 terms of the series. That's exactly what we got in problem 39, right? Oh, I'm sorry. I didn't change the series. So I really want -1 to the n over n factorial. So this is just interesting, but okay. So for problem 39, this was the series. Theorem 915 says that for any series, the nth partial sum approximates the sum of the infinite series with a remainder or an error no bigger than the absolute value of an plus 1, right? That's theorem 9.5. So in this case, I want the series minus 1 to the n over n factorial. So let me just change that. Minus 1 to the n over n factorial. That's my new series. And for example, if I were to calculate the first 6 terms, that's what it is. Sorry, it should be minus 1. Oh, minus 1 to the n over n factorial. Okay. Let me just double check. Oh, and I want to start at 0. All right, so, okay. Problem 41. So we're going to use theorem 9.15. And we're looking at this series, and this is the capital Nth partial sum. And the book actually tells us what the sum of this series is. It's 1 over e. But we want to figure out how many terms do we need to approximate the sum with an error of less than 0.001. So the nth term is going to be this, and if I take 60 terms, that's way too big, much more than I need. Let's take 4th. Oops. Yeah, if I take 4 terms, if I take the 4th term, it's 1 over 24. If I take 6 terms, it's a little bit bigger than 0.001. If I take 7 terms, it still is big. Oh, 0.0001. So if I take 7 terms, the error is going to be less than 0.0001. Let me just double check. So so the 6th term of the series is bigger than 0.001, but the 7th term is less than 0.001. So I can choose n equal to 6. And if I take the sum of the series of the first 6 terms, I get that. What is that as a decimal? It's that. What is the limit of the series? 1 over e. So what I really want to know is, what is the difference 1 over E minus S of 6. Make this absolute value. Uh-huh. So all right, so this is problem 41. You want to know how many terms you need to take from this infinite series to approximate the limit within 0.001. And we just have to find out what term of the series in absolute value is smaller than 0.001. And the sixth term is bigger than 0.001, but the seventh term is smaller than 0.001. So capital N is equal to 6. And the sixth term of the series, the sum of the first 6 terms of the series is 0.6. And the error between that and 1 over E is smaller than 0.001. So the answer is N equals 6. And I use the graphing utility, that is Maple, to actually calculate this partial sum. Here it is. And I compared it to the limit, and this is the difference. So that's what's going on. Any questions about that?
I think I understand it now. We
I mean,
just,
it's really, you can't do the problem without having a very good understanding of the theoretical material that's behind it.
mhm. Yes. So the difference between the sum, which is 1 over E minus 6.
Well, the whole sum is, let me put it in here. The sum from 0 to infinity, that's 1 over E.
Mhm.
Right? The sum of the infinite series is 1 over E. And what we're finding is how many terms of the series do you have to take? So you have the sum of that series is very close to 1 over E, and the error is smaller than 1 in 1,000. 1 over
Oh.
0.001.
Okay. Yeah, that makes sense now. Yeah. Okay, I was just taking some notes. Okay, okay. Um, can we do 50? The same page?
Sure. Let me just get back to this share screen. But for some reason, I don't know, something's the matter with my Maple. It's not allowing me to move down. I don't know why. Let me see if I can start up here again. So you said which problem?
50.
Okay. So for problem 50, we have a series where the nth term is plus or minus 1 over n to the 5th. So let's say we let a be the function n goes to minus 1 to the n plus first power divided by n to the 5th. And we want to find the number of terms to approximate the sum of the series with an error of, again, less than 1 over 1,000. So we want to find n such that an plus 1 is less than 0.001. So let's try and do it like this. For n from 1 to, I don't know, let's go up to 6, do. And what I want to do is evaluate a of n. So if a of n is less than 0.001, then print n. So I'm just writing a little loop. So Maple will find the first n for which this number is less than 1,000th. Oops. If I need a parenthesis there. Aha, oh, that's weird. So I should have said absolute value. absolute value of A of n. So starting with 4, maybe I should make this n plus 1 actually. So when n is 3, A4 in absolute value is less than 0.001. So we just want to choose n equals to 3. And so that's the answer. We just need 3 terms. But just to check, I'm interested in the sum of A of n. N goes from 1 to infinity. That's right, as a decimal. So if you sum this infinite series, you get this number. And what happens if you just sum the series from 1 to 3, you get this number. And the difference I subtract in absolute value is less than 0.001. So I only needed 3 terms from this series to approximate the infinite series with an accuracy of 1/1000. Even better, actually, but certainly this is less than 1/1000. Okay, in the same set, problem 56.
Yes.
Oops, what happened there? Problem 56. Oh, determine whether the series converges conditionally or absolutely or diverges. So let's just write down the series. So the series is the sum of, and what is the expression? It's -1 to the n plus 1. N plus 1 divided by n plus 3. And let's just see if this is the right. Oops. This is supposed to be -1. So problem 56, yeah, that's what it is. But I use a capital S, so that's just telling me what the problem is. If I change the capital S to a lowercase s, it tells me this alternating series converges to this number, right? So the series converges, but does it converge absolutely? So if I take the same series, but I take the absolute values of the terms, that means I just replace this plus or minus 1 by a 1. So this is this series, but the absolute values of the terms, it diverges. So the series in 56 converges conditionally. It doesn't converge absolutely. This series diverges when I take the sum of the absolute values of these terms, but the alternating series converges. So this is a conditional convergence. So what we see is the series converges conditionally, but not absolutely. All right. Is that okay?
Yes. Let's see. Now from page 648, I want to do a couple of problems.
Sure.
So first one will be problem, let's do 66.
Okay.
66.
Weird. Something's the matter with this maple. So page 649.
48.
648. Problem, which problem?
66.
66. So okay, well, of course, maple will tell you right away whether it converges or diverges. But in this series, the nth term, I'll write it as a function. So a of n is going to be minus 1 to the n times 3 to the power n divided by n times 2 to the power n. And for example, the ratio test says that if you have a series and the ratio of successive terms is greater than 1 or goes to infinity, then the series diverges. So I want to take the limit of a of n plus 1 divided by a of n as n goes to infinity, right? I want to know what this is. Oops, this is backwards. That's not good. A of n plus 1 over a of n as n goes to infinity. I need to know this limit. So when I write it limit with a capital L, it just states the problem. So I need to use a lowercase l. And this limit, and I should be taking the absolute value. The limit is 1. So if the limit is 1, the ratio test is inconclusive. But something about this isn't right. Okay, this is better. So here is the nth term of the series. Here I take the ratio of the absolute values of consecutive terms. The limit is 3/2. If the limit is bigger than 1, the series diverges. By the ratio test, the series diverges. I mean, you could do this by hand, but I'm just having Maple do the calculation.
It's way easier to do it in Maple. I've been doing it by hand.
Oh, yeah, no. So it's easier in Maple if you can program it in Maple correctly. If you
Yes.
make a mistake programming it, you're stuck. But once you get over the hurdle of knowing how to write these problems in Maple, it's very quick.
Yes.
Let's also try the root test. In the root test, you take the nth root of the absolute value. So you have the absolute value of A of n raised to the power 1 over n. And we want to take the limit of this as n goes to infinity, right? So this is the limit of the nth root of this number. And that limit is also 3/2, which is bigger than 1. So we can also say that by the root test, we also know the series diverges.
Okay, yeah. I get it now. Let's see. Now just the one last problem.
Sure.
Let's do 76.
So problem 76 we have a series, sorry, problem 76. We also have an alternating series, and so this is page 648, number 76. Let me call the terms of the sequence, well, no, I'll call the terms of the sequence B's for a change. So B will be the sequence defined by V of n is equal to, or the book is using the letter K. K goes to -3 to the K divided by the product of the first K plus 1 odd numbers. So let's see. Let me just double check. I forget whether product is spelled with a UCK or not. PROD. Product. Yep, good. So this is the product of the numbers 2 times I plus 1. I goes from 0 to K. So that looks exactly like what we're dealing with in problem 76. And we want to approximate the series with an error of less than 1 in 10,000. So I want to know, when is this number in absolute value less than 1 over 10,000, 0.0001. So I can say for n from, I don't know, let me use a capital N from 1 to, I don't know, 10 do, and do, and if the absolute value of V of n plus 1 is less than 0.0001, then print n. And if. Let's see what happens. So it looks like B9 is less than 1 over 10,000. That is when capital N is 8, B9 is 1 over 10,000. So let me just make this an 8 so I don't take up so much space. So the first number where the nth term is less than 1 over 10,000 is the 9th term. And so that's the answer. The number of terms required to approximate the sum of the series with an error of less than 0.0001. And let's just check out what it is. So suppose I take the sum of B of K, k going from 1 to 8. That's what it is. Let me get this as a decimal. Mhm. And suppose I want the infinite series. Sum to infinity. This is just this is some imaginary error, but these two numbers agree to less than 0.0001. That is, if I take the difference, it's less than 0.001. So let's go back into it like this. Yeah. So this first number is the sum of the first 8 terms, and that's within 1/10,000 of the true value of the sum of the infinite series. Yeah. That's what it is.
Okay, so it's, yeah, the same thing as the first exercise, right?
Yeah, they're all similar. I mean, it's just interesting to see how to solve these problems using Maple.
Yeah. So, yeah, I think that's it. Thank you.
Okay, glad to help. Take
I'll
care.
see you another time.
Sure, bye-bye.